called a ballistic pendulum problem, and it's a classic problem in conservation of momentum. What we have happening is a bullet, and we don't know its initial velocity. That's actually what we're going to try to find. So a bullet that has some unknown initial velocity slams into this wooden block here, sticks to it, and then the two of them swing upward to a maximum height. In this case, it's 0.16 meters. Based on that information, you should be able to figure out the initial velocity of the bullet. And I based the numbers from this question on a video that I found on YouTube where somebody actually performs this experiment. And if I can figure out how to create a link to that within this video, I'll do that for you. Otherwise, you can just look up, ballistic pendulum, and maybe you'll find it. Anyway, let's take a look at what's happening in this situation. The way I look at these problems, we have three distinct locations and points in space and time. So right here is what I would call A. And to be clear, A is before the collision, before anything happens. Then let me just jump ahead to C. C is really at the maximum energy transfer point. At this point, it's at the highest point. And then what's B? Well, B, and it's really important to understand what B is. That what happens here is the bullet sort of penetrates into this block, and eventually the bullet comes to a stop within this block. And that happens extremely quickly. And so B is the moment, the exact moment that the bullet comes to a stop relative to the block. And I say relative to the block because at that point, the bullet and the block together are moving. The bullet has transferred momentum and velocity to the block. So B is right after bullet stops relative to the block. And here's the other really important thing. The only way to solve these problems is to assume that this happens so quickly that it's also before any significant upward swing. So basically, A and B are essentially the moments right before and right after the collision. If you compare A and B, you can use the law of conservation of momentum, because you can use the law of conservation of momentum anytime the only forces that are involved are forces that the objects that are in your equation are exerting on each other. And here we're really just looking at the x direction. So gravity isn't a factor. It hasn't begun to swing up significantly. We're just looking at the x direction. So we're just thinking about x direction forces. And during this collision, the only x direction forces are forces that the bullet and the block exert on each other. Those are called internal forces. Because of Newton's third law, they're equal and opposite. They cancel out. And so we can use law of conservation of momentum. Now here's something that's extremely important. It's extremely difficult to use the law of conservation of energy, what I call UCWC. It's extremely difficult to use UCWC during this time. The reason is right in here, as the bullet penetrates into the block, there's a lot of force that's a non-conservative force. And so we don't have any idea what to put in for that W into the UCWC equation. It's a complete and utter unknown. And that's what makes it very, very difficult to compare UCWC. A lot of energy transfers into heat in this process, and we just don't know how much that is. So don't use UCWC between point A and point B. However, between point B and point C, it's the exact opposite situation. We can use the law of conservation of energy because the collision's over. The non-conservative force is in the past. Now it's just swinging upward. So the only significant force that's acting on it is gravity. Gravity is a conservative force. And so the energy that it has right after the collision is going to be the same as the energy that it has at the highest point. Different type of energy, but it's the same. And no energy is lost to heat or other things of that nature. Now, we can't use the law of conservation of momentum here because gravity is a significant external force. this block loses momentum because gravity is taking it away. And gravity is being exerted by the Earth, so it's not an internal force, it's an external force. The Earth is an external object that's coming out and exerting a downward force on these things. There are many, many problems that you'll encounter that are like this, that have a point A, B, and C. They don't always have something swinging up into the air. Sometimes they'll, after this collision, this thing will slide into a spring. It's the same deal. The energy turns into elastic potential energy instead of gravitational potential energy. You can even have the object sliding to a stop through friction. And essentially, it's the same deal with A, B, and C. Maybe I'll take a look at those in another video, or if we have time at the end of this video. But let's go ahead and solve this problem. So let's look at the what happens between A and B. So there I'm going to use the law of conservation of momentum. So that means I'm going to take the mass of the bullet, which is 2.6 grams, times the unknown velocity of the bullet, plus the mass of the block, 613 grams. Initially, it has a velocity of 0. Now, these two things become stuck together. It's an inelastic collision. So afterward, I'm going to do 2.6 plus 613 times the velocity right after the collision. I'm going to call that VB. And actually, maybe I'll call this VA just to be consistent. Now, some of you might be saying, why didn't you convert this to kilograms? Turns out that in this equation, converting to kilograms would mean dividing both sides by 1,000. And since I'm doing the same thing to both sides, that effect would cancel out anyway. So you can convert to kilograms if you want to, but you actually don't have to for this particular equation. Anyway, I have two unknowns, so I have to pause to figure out one of those unknowns. Now I'm going to look at between B and C, and that's where I can use the law of conservation of energy, or as I call it, UCWUC. So, very important, we're looking at the energy at B, not at A, but at B. And so the energy at B is the kinetic energy due to this right here. So that's 1/2 the combined mass times the speed at B squared. And that's the only type of energy it has there, especially, and it makes sense to do this, if we call this lowest location where y equals 0. So there's no gravitational potential energy there. On the other side of the equation, we're going to have gravitational potential energy, 2.6 plus 613 times 9.8 times 0.16. And actually, I'm not going to have any kinetic energy because the thing that makes this the highest point is that it temporarily stops at that location. So that's it. Those are the only types of energy. And again, you might be saying, why didn't you convert this to kilograms? Well, look, we've got the same thing on both sides of the equation, so it cancels out. So this allows us to figure out the speed at B. This is the speed right after the collision. So let me get my calculator here. 9.8 times 0.16, multiply by 2, take the square root. 1.77 meters per second is the speed right after the collision. So now I can use that information and bring down this equation where I had that unknown and see what happens. So I have 2.6 VA on the left side, and on the right side I have 2.6 plus 613 times, now I know the number is 1.77. So I can find out what the speed at A is equal to, and let's see what I get. So 2.6 plus 613 multiply by 1.77, divide by 2.6, and the answer that I get is 419 approximately meters per second. 419, let's say, meters per second. And that's the answer to our question. Let me give you a follow-up here. A very, very common follow-up is, how much energy is lost to heat and other forms of energy as a result of this collision? So that's where we actually can go back and use this equation right here, and the energy lost is just equal to the work done by the non-conservative force. So now that I know all these velocities, I'm going to go back to this equation and solve for the unknown W. So maybe I'll do that on this side of the page. So I'm actually going to take a look at A. That's where it had all the energy. And I'm going to compare that. I can either compare it to B or I can compare it to C because it had the same amount of energy at B and at C. So it really doesn't matter which of these two I compare it to. I just want to go from A to some other point because between A and B, That's where the non-conservative force created a lot of heat. So at A, the energy is just the energy of the bullet, 1/2. And here, I'm going to be careful about converting to kilograms. It may or may not be necessary, but it's the safe thing to do. So 0.0026 is the kilograms of the bullet, and 419 squared. That's the total amount of energy at A. Why don't I compare it to C? I think that might be the easiest thing to do. At C, we had the two things added together. So that is 0.613 plus 0.0026 times, sorry, this is mushed up, times 9.8 times 0.16. Oh, and you know what I forgot? Forgive me for this. On this side of the equation should be plus WNC, all right? So I have the potential energy at A is 0. The kinetic energy at A is this number right here. Can't forget the W because there is work being done by a non-conservative force between A and C. And then on the other side of the equation, there's potential energy at C, but there's no kinetic energy at C. So sorry I forgot the W and C, but anyway, let's see what we get as an answer here. So if I multiply, let's multiply these numbers together first. So 0.613 plus 0.0026 times 9.8 times 0.16. And so that's 0.965 approximately. And the units there would be joules. That's why I wanted to convert to kilograms, because unless I convert to kilograms, I'm not going to get joules. Then I'm going to have to subtract over this from the other side. So minus 419 squared times 0.0026 times 0.5. If I did that right, that's 228 joules. Look at that incredibly huge difference. I'm going to subtract them. So basically, it's a loss of 227 joules. Huge amount of energy that went into creating heat and damage at this location right here. And this is why you cannot say that the energy at this location is equal to the energy at that location. It simply isn't, because of all of that work by a non-conservative force. All right, I think this video is long enough, so I will continue with some other scenarios that are similar to this on a follow-up video.